Alright, today we're going to talk about the maths of vectors. Bothered writing mathematics, so we'll stick with maths. Okay, so a vector is a quantity that has both magnitude and direction. So it's not just a number, it's got a direction associated with it. Sometimes the direction is important. Okay, the position doesn't matter so much for a vector, although we're going to talk about what position vectors are. But once you've defined it in that position, we can move that vector around and it will still be called that, whatever we've called that vector, as long as it's going in the same direction and has the same magnitude, it will still be the same vector. Okay, so we'll jump straight into it. So a position vector, this is notational wise. Okay, so let's call this point A and this point B. We can have a vector that is the length from A to B, or magnitude, and that's represented by this arrow. Okay, so the length of the arrow is how big the vector is, and its direction is whichever way it's pointing. So it's pointing this way, so got a direction there. Okay, so the way we write that vector down is we say from A to B, we've got a vector, we put a little arrow on top. Okay, back when I was really cool, there was a time when that was the case, self-proclaimed coolness. I never used to put the bottom arrow on there because it's the way I like to roll and just leave it like that. Not these days though, I'm a bit old now, so I go back to the arrow on top, the full arrow. Okay. Or we can have the variable notation. So we can just call it a letter, any letter we like. Let's call this A because it's a bit long to write this A, B all the time. And then to indicate that it's a vector, I put what we call a tilde underneath, a little squiggly line, and then put that little squiggly line underneath the tilde to indicate that's a vector. Okay, so we've got two notations, we've got this variable notation and this position notation, A to B. We've got this vector here. Okay, so what can we do with these? We could add them. Let's do some addition. Vectors, addition. Add up two vectors. So if we have 3 points, we need two vectors. Let's go with 3 points. Here we go. We've got A, B, and C. Okay, so we've got vector A, B, and vector B, C. So if you write it out in the position notation, this is the good thing about the position notation. We go from A to B. We're back to the old way of doing it. Oh yes, let's, for old time's sake, let's do this. A, B plus B, C. Right? A to B, and then B to C. So if I travel from A to B, then from B to C, obviously that has to be the same as going from A to C. Okay? So I could draw this vector in here. So we call this vector here the result of adding these two vectors together. Right? Another way to think about it is in terms of physics. So if you think of pushing this way, someone pushes this way, someone pushes this way at the same time, with this one pushes in this direction, this has a bigger magnitude push, but smaller push, but in this direction, that would result in having, it would be the same if you replace these two with one big push in this direction. Okay, so you would have the same result then. So this is called a resultant vector. Resultant, yeah, that'll do. Resultant vector, or sometimes I call it net vector. Net vector. So if you're in physics and you talk about the net force, that is the sum of the forces that has the result of in this direction or whatever. Okay. We could also call these, if I call this one A, this one B, then this vector here is the sum of A plus B. Okay, so I could write it like that as well in variable notation. Okay, subtraction. What do we do with subtraction? One thing I forgot to mention is on these vectors, well, we talked about the magnitude being the length, the direction being the arrow. this graphical geometric interpretation, the arrows. Okay, so we've got the head of the arrow, the head of the vector, and this is the tail of the vector. So when you add vectors together, you always have to add them head to tail. So the head of this vector has to add to the tail of that. It already made sense with this one, but if I do a subtraction, let's do a subtraction. What if we have, I'll write this in blue, whatever, subtraction. I'll start here with A, B, and C. I don't know why I don't give myself more room, but I do. Here's my A. Here's my B to C. So now I want to do A to B minus B to C. Do one of those ones. A to B minus B to C. What's that going to be? So minus B to C, A to B, that's going to be plus the same as the negative of B to C. And the negative of B to C is C to B. Okay, so it's like flipping the vector around, going the opposite direction. So it's going to be the same as adding C to B. But C to B, if I drew a C to B in, C to B is an arrow that's pointing ahead of this arrow. So when I add the vectors together, I need to add them head to tail. So I'm going to draw it down here. It doesn't matter where you draw it. So I'm going to give you that. Get rid of the point because I'm not moving point A. I'm just moving the vector, and that's okay. So A to B plus C to B. Now C to B goes this way and is this long. C to B goes this way and is this long. Okay. So the resultant vector now is this one. Okay. All right. I've got no point out here. Maybe this is point D out here, and I could write that it's the same as A to D, but I've got no point to define what that is at the moment. So it's better to have the A and B because I had to for these two. So it's A minus B, yeah, and minus B to get that. Okay. Go A minus B. So that might be a more convenient way to write it. Alrighty, let's talk about a few other things. So, what can we find with the vector? Sometimes you'll have to find the magnitude of the vector, which is obviously given by these symbols. Sometimes I might say it's in complex numbers, but now I've got a vector in there. So the magnitude of the vector A, B, it's just its length. Okay. Let's do. What can you do with these? Let's do a little vector proof. Okay. Okay. So let's have a scenario. Our scenario is we've got a parallelogram OABC. Like this. Okay, we know this is a parallelogram. This is O, A, B, C. Generally, we label going around anti-clockwise, O, A, B, C. Okay, so we know we've got a parallelogram, and on that parallelogram, we're going to call OA. Let's call that A. Let's call that B. Now, because it's a parallelogram, I know that that's this way and this way. I know that OC is also equal to B. Right? It's the same vector. They're parallel and the same length. And CB is the same as OA. So this can also be called A. Okay. Let's define a point here, a quarter of the way along OA. So 1/4 of OA, which is A. 1/4 of the way along A is the same as OP. So we've got a point P, 1/4 of the way along, might be there. Call that point P. Okay. And we want another point D, right? From this point P, right, is, I'll just dot this line out, 1/5 of the way from P to C, 1/5 the way we're going to call D. So 1/5, so we haven't even started the question yet, I'm just setting it up. 1/5 of, now I've got no A and B's for P to C yet, so I'll just say P to C. 1/5 of the way P to C is P to D. Okay. We've got this information. All right. Now we want to show that ODB are collinear. Okay. So the collinear means that all these points lie in a straight line. So these 3 points, we want to show that it lies on a straight line. How do we do that? Okay. So we need to show that OD, yeah, if we scaled that up some, we'd get to OB. That's the same as OB. So if we made a scale factor of OD, we'd get up to OB. Or the other way around. If you had OB and you scaled it down by a factor, you get OD. And that would prove that they're on the same line. Okay? So let's work that out. Okay, so if we've got we need to find OD basically, or even OB. We've got OB. OB. Well, that's the same as A plus B. We already know that. Okay. So O to A to B, OB is the same as A plus B. That's just vector addition, just did before. Okay. So let's go. How do we get from O to D? Well, we can go O to D. That's the same as O to P plus B to D. O to P plus P to D. Okay. That's a P, that's a D. Okay, so we already know what OP is. OP is quarter of the way along OA. So we've got quarter of A along OA plus we want 1/5 of the way along P to C. So 1/5 of the way along P to C. Okay. So how do we get from P to C? Well, in terms of A and B, we want to go back along this way, a quarter backwards all the way along OA, and we want to go up B. So what have we got? 1/4A plus 1/5 of negative 1/4 A, negative 1/4 A, plus the whole of B. Yeah. Okay, so what does this come out to be? I've got 1/4 of A. Well, let's do minus because we're going to expand this out. Minus 1/20th of A plus 1/5 of B. So what's 1/4 minus 1/20th? Okay, so this is 5/20ths minus 1/20th is 4/20ths. 4/20ths is 1/5. 1/5 of the way along A plus 1/5 of the way along B. Take out 1/5 as a common factor. 1/5 of A plus B. Now A plus B is OB, and we're 1/5 of the way along. So 1/5 of OB is O to D. So we've proved that OD must be on the same line as OB, therefore collinear. So we want 1/5 of OB, and then that's as required. Yeah, we've proved that they're collinear points. Okay, that's it for this video.